look at the question that's on the board. The top one, we should be kind of, au fait with how to do. Am I right? How would you calculate the probability of obtaining 3 6s when rolling a fair die 3 times? How would you do it?
1 over 6 cubed.
Yeah, 1 over 6 cubed. It's a sixth for the first 6, a sixth for the second, and a sixth for the third. And we're going back to that GCSE idea of something and something and something. We're multiplying probabilities together, and they are independent events. So that is the correct way to do it. And as Jack said, we've got 1/6 cubed, which would be what, 1 over 216. Yeah. What's the probability of obtaining 2 6s?
1 over 6 squared times 5 over 6 times 3.
Ah, right. Why times 3? So you said 1 over 6 squared times 5 over 6 times 3. Why 3? Explain.
Because there are 3 ways in which you can get 2 6s when rolling a fair dice 3 times.
Absolutely. You could get a 6, and then not a 6. You could get a 6, and then not a 6, and then a 6, and then you could get not a 6, and then 2 6s in a row. Okay, so we know that just from thinking about the experiment. All right. 2 6s first, a 6, not 6, then a 6, not 6, and then 2 6s. And the probability of each of those 3 is the same, isn't it? Like you said, we've got 1/6 multiplied by 1/6 multiplied by 5/6. And we know at dice, we know that the probability of not getting a 6 is 5 out of 6 because there are 5 numbers that are not 6, right? And that's absolutely right. Okay. How could you evaluate that 3? Where did that 3 come from? We know it came from this experiment because we can list all of the outcomes. What happens if it's got just too many to list, Jamie? Yeah, that's right. This 3 is actually 3 choose 2. Okay, directly linked back to that binomial expansion. 3 choose 2. 3 rolls of the dice. We want 2 successes. Right? We're going to be talking a lot about successes and failures for this. So we've got 3 rolls of the dice, 2 successes. So we've got 3C2 multiplied by 1/6 squared multiplied by 5/6. Notice the powers, 2 plus 1 is 3. This is exactly the same, isn't it, to the binomial expansion? It's just that instead of A plus B, we've got 2 different probabilities. And the link is really that if you've got this A plus B to the power of n, where n is a positive integer at this point, it's almost like saying A is going to be success and B is our failure. And when we combine success and failure together, we get 1, and 1 to the power of anything is just 1, because what's the overall probability of everything after you've exhausted all possibilities? Is 1. Right? So we're going to use that. That's it. It's the binomial expansion, but instead of letters, you've got probabilities. So let's look at this question. So, anybody want to kick off? And it might be about saying what's the probability of success, what's the probability of failure, how are we defining success? What is a success in our experiment? 3. Yeah, okay. So it's a bit odd, that, isn't it? The success is actually him being late, isn't it? So we've got this probability of 0.4 of James being late home from work on any day. Yeah. What are we going to do with that 0.4 when we calculate? Yeah. Okay, so I'll stop you there. You can just use 0.4, it's absolutely fine, but 4 over 10 is a fraction of 0.4, but we're going to cube it, aren't we? Late, late, late. Now, if we just did 0.4 cubed, that's just the probability of being late 3 times in a row, isn't it? But we're talking about a 5-day week, so I might have interrupted Sri there, but what are we going to have to multiply that by for the 2 days, sorry, for the 2 days that he's not late? Yeah, 0.6 squared. Now this calculation here describes James being late Monday, Tuesday, Wednesday, and then on time Thursday, Friday. Right? But what about being late Monday, on time Tuesday, late Wednesday, Thursday, on time Friday? Right? So we need to work something else out. 3 again. Exactly right. So it's 5 days in the week, choose 3 lates. Right? So this is the number of ways that you can be late 3 times out of 5 days. This is the probability of being late 3 times, and this is the probability of being on time twice, effectively. All right? Look at the powers. 3 plus 2 is 5. We're all good. What does that work out as? 0.2304. Can I get a corroboration from anybody else? Yeah, brilliant, excellent. And 4 decimal places for a probability is good. We like 4 decimal places. Right? It's a good rule of thumb. So it's pretty straightforward, right? The thing to notice is the reason that this is a binomial is because there are only 2 different things that can happen. Right? Just like the binomial expansion, you had 2 terms in a bracket. There's only 2 things that can happen here. In terms of our experiment, James can be late or James can be on time. Early doesn't matter. It falls into on time. He's either late or he's not late, in fact. Right? Late or not late. 2 different things. Binomial. Okay? Probability of one, probability of the other. The sum of those 2 probabilities is 1. And those are the conditions that create a binomial distribution. So here in general is a formula for the binomial probability distribution. And you can see that they've used the NR column notation for NCR. All right, so just get used to seeing that. I don't particularly prefer it at all, but that's there. And this notation at the bottom is what I want you to be writing basically for every question. All right, we have X, capital X, just like discrete random variables. That is our random variable. It's the outcome of an experiment. The little tilde symbol means is distributed. The B literally stands for binomial, because when we do normal distribution later on in the year, you'll have a capital N there. It just describes the distribution. And then inside the brackets, N is the number of trials, and P is the probability of success. Okay. So for our last experiment, James and the lateness, we had a discrete random variable X, binomial distribution. There were 5 trials because there were 5 days in the week, 5 opportunities for an experiment, if you like. The probability of success, we defined success as being late, which was 0.4. So this notation here describes the question that we just answered. All right? Now, the binomial distribution is also a discrete distribution. James couldn't have been late 3.7 times in the week. It was either 3 or it was 4. Right? In case you're wondering, there aren't only discrete distributions. There are continuous distributions. The only one that we'll study this year is the normal distribution. It is a continuous distribution. But we'll come back to that a bit later. So that's the general stuff. That's like the textbook stuff. I want you to have a go at that question. All right? Probably won't take too long. 25 dice are thrown. Find the probability that 3 6s are obtained. Let's have a go at using the notation X tilde the brackets, all right, to describe the number of trials and the probability. Let's see the full calculation written out, NCR, probability, and then work out the answer. Gordon again. So you've had a couple of minutes to have a look at it. There is our answer. And this is how you should really be setting out your working, okay? Notice I've got the X my discrete variable is distributed binomially with 25 trials. The probability of success is 1/6. Okay, you don't always have to use decimals. If it's more convenient to put a fraction because you'd have to round the decimal, use, oh, what happened there? Use the fraction. There we go. And then this, the probability that x equals 3. That's what you are evaluating. What's the probability that the outcome is 3 sixes? And it's 25C3 multiplied by a 6 to the power of 3 multiplied by 5 6 to the power of 22. 0.1929 to 4 decimal places. Okay. All right. So it's not too difficult, is it? Yes. Pretty straightforward. And quite fun, I think. It's really different to all the other probability stuff you've done. I think this is quite interesting because anything to do with combinatorics and it absolutely it fascinates me. Right, so we need to be aware, and this is quite a common sort of part A or part D or the last part of a question. Give 2 reasons why this distribution is appropriate for the model or for the experiment that you've been suggesting in the question. And these are the reasons, all right? A binomial distribution needs a fixed number of trials, okay? There has to be a set number of trials. That's what the n is. And you use that n in your experiment, NCR, okay? In your calculation, sorry, NCR. So you need n as a fixed number of trials. Each trial has the same 2 possible outcomes, 2 outcomes binomial, and they have to be the same all the way through. Can't change. The outcomes of the trials are independent of one another. They must be, all right? They must be independent. There can't be any overlap. It's either this or it's this. That's it. There's no this and this together, right? And the probability of success remains constant. Now, I would say that if you ask that question, explain why a binomial distribution is a suitable distribution to model this situation, they're going to want 2 of those, all right? And the 2 that I generally go for, fixed number of trials, and they're independent of one another. Those are the 2 that I would put down. Easy to remember. Done. All right. Okay. This is where we're going to have a look at calculators, because I mean, if we read the problem, no context here. We're not told what the experiment is, but we can infer from the notation that there are 5 trials. The probability of success in each trial is 0.35. Yeah, that's it. Whatever this experiment is, we've got all the information that we need. Now, for part A, sure, to find the probability of x is less than or equal to 3, you could find this. I mean, I'm already bored of writing it, to be honest. You could find that. Each one comes with its own NCR calculation. Yeah? You can imagine how long that would take. Right? And that's only less than or equal to 3. Imagine I'd asked you less than or equal to 15 when there are 35 trials. Okay? This is where we use what's called the cumulative binomial distribution function on your calculator. All right? And so let's have a look then at how that works. CG50 people first. Sorry, class whizzes, but CG50 people first. What you're looking for, menu 2, statistics. Okay? When you're on menu 2, you've got the table in front of you. F5 says dist, that's for distribution. When you get to distribution, you're going to go binomial, it's F5 again. Okay? Not on the class whiz chip, I'll do the class whiz in just a minute. And then you've got BPD, BCD, INV. Let's get into the habit of only ever really using BCD. Right? You're never going to use INV because we don't do the inverse binomial. You can use BPD, which I'll explain when we go on to question B, but BCD, cumulative distribution. And cumulative, we want all the probabilities from 0 up to 3. So press BCD. The data should say variable, and then you ask for lower and upper. Now, this is where this calculator is too clever for its own good. The binomial distribution can be modeled as a curve. Okay? And effectively what you're doing here is you're finding an area underneath that curve. So here's 3. We're trying to find the area under that curve all the way down there. Now the problem with, not the problem, but the thing you've got to know about this curve is it never quite reaches the x-axis. Okay, it keeps going on forever. So there's no lower value, right? Not for this type of question anyway. If we were doing a question where x was greater than or equal to 2 but less than or equal to 5, sure, you have a lower and an upper. But when it's just less than or equal to 3, our lower is technically way down negative infinity. So get into the habit of just choosing a large value. I use 100,000. So my lower is going to be negative 100,000. All right? Because it's so far down that way that any area that's being added to it is negligible. And then your upper for this one is going to be 3. We need to find the area between that minus 100,000 and 3. And then num trial, number of trials, right? Probability 0.35. Keep pressing XE, and then you're all good to go. Did everybody get 0.9459 or 9460? Yeah? 9460. Happy with that? Pretty much know what you're doing? Okay. Class whiz, people. I'll just get the class whiz out and have a look at it. You're from the calculator menu, right? So go to your menu, and you need to go to option 7, which is distribution. Now, when you're in distribution, you've got 4 options that are present at first. None of them is the one you want. Okay, so you need to scroll down. So use your cursor to scroll down, and then option 1 has changed into binomial CD. That's the one you want, binomial CD. So press the 1. You're going for the variable option. We don't need the list, we're going variable. And then you've got 3 things to fill in, x, n, and p. And arguably, it's simpler on the class whiz because you've got less control over it. So your x value is just that. You don't have to worry about the minus 100,000 or anything like that. Okay, your x value is just that 3. The number of trials is, n, so it is the number of trials, which is 5, and p, 0.35. And you get exactly the same answer, 0.9459775, which we'll use for 4 decimal places. Okay? Yeah? All right. Now, you'll get practice at this. This is what we're doing in this lesson, right? You might be thinking, well, why did he show us the calculation? What on earth is the point of doing the calculation? You need to know the calculation, all right? I'm not an exam writer, but they will think of clever ways to force you to use that calculation that will catch you out if you try and do it with a calculator, okay? But anyway, my recommendation is whenever you have a probability that x equals something, you use the NCR calculation. It just means that that calculation is never lost, and you always do it. So if it's less than or equal to, use your calculator. If it's greater than or equal to, use your calculator. If it's simply equal to, do the calculation. All right? So the calculation for this one is going to be 5 choose 3, 5 trials choose 3 successes. 0.35 is the probability of success cubed because it's 3 successes, multiplied by 0.65 squared because that would mean that there are 2 non-successes. We'd work that out. So you have to go back to the calculator menu for this, but we've got 5c3 times 0.35 to the power of 3 times 0.65 squared, 0.1811. Everybody agree? Did I do it right? Nobody? 0.1811?
Yeah.
Cool. So now, just because I feel like it would be unfair if I didn't, you can do this on your calculator. So go back to your distribution. And this time, instead of choosing binomial CD or BCD, choose binomial PD, probability distribution. For the class whiz people, it's in the distribution menu and it's option 4 without having to scroll down. And then you go to variable and you input the same 3 things. For you guys, BPD is there and you don't have to worry about any lower limit. You just type in the x value. So x equals 3, x equals 3, 5, and then 0.35. And does it come out with exactly the same answer? Yes, it does. So your calculator can do it, right? It can do it. But the reason I say don't do it is because, one, as I said, who knows? Somebody might think up some sort of devious question where you really need that calculation on instant recall. And if you've not practiced it, it's not going to be there. And secondly, I don't want you sitting in the exam and using binomial PD for a less than or equal to question. Do you see what I mean? Because these things can happen in the heat of an exam, all right? And you've got no way to check. And if you can't remember, oh my God, it's just too stressful. So I recommend, honestly, for equal to questions, do the calculation. Right. Probability that x is greater than or equal to 3. CG50 people, you can probably imagine your lower and uppers are going to basically switch around. Your lower limit is going to be the 3. Your upper limit is going to be positive 100,000. So calculate that way. For class-ways people, sorry, you've got a little bit of extra work to do. Right? And it's just this, basically. Imagine a number line. 2, 3, 4, 5. There's only 5 experiments. 5 trials, sorry. For anything greater than or equal to 3, yeah? I mean, include the 1. You are looking for the probability from 3 onwards, aren't you? Follow that? You're looking for the probability of 3, 4, and 5. Now, your calculator doesn't do that. Sorry. Your calculator only works out less than or equal to. So we need to turn greater than or equal to 3 into something to do with a less than or equal to. Now, come on, Jacob. Perfect. We're going to do 1 minus the probability that x is less than or equal to 2. So do you see how, because this is discrete, greater than or equal to 3 leaves out anything less than or equal to 2. All right? And as the probabilities need to add up to 1, we just do 1 minus this bit. Okay, 1 minus this chunk to the left gives us the chunk to the right. All right? Okay. And I think the added thing is you're going to have to just do probability of x is less than or equal to 2, store it, and then go back to the calculator screen and do 1 minus your answer. Something like that. I don't know if the answer button works for probability distributions. But just work it out using your calculator, see if you can get it to work. What is the answer to that out of interest? 0.235, 4 decimal places? 2. Cool. Have we got corroboration? Tom's nodding. Yeah, cool. Okay. All right. So that's using the calculator. Now, there's nothing else to it, other than the language that they'll use in the question. So if you look at the left-hand column of that table, you can sort of picture the questions. What's the probability of this being greater than 5 or at least 7? That's how they try and trick you, isn't it? That's you've got to interpret that language and know what it is that you've got to do. So the probability of greater than 5 means the probability that x is greater than 5. But neither the CG50 or the class whiz will calculate that for you, because they only deal with, in the case of the class whiz, less than or equal to, and the CG50 greater than or equal to, you can do as well. We're missing an or equal to. So we have to convert the question. If it's greater than 5, what are you actually going to turn that into? Go. Okay, so for those using the CG50, we're doing the probability that x is greater than or equal to 6. We need the or equal to, or your calculator will return the wrong answer. For those on the class whiz, if it's greater than 5, it's always handy to draw a number line for these. Seriously. If it's greater than 5, it's all of those numbers. So for the class whiz people, you're going to have to do 1 minus something. What are you going to do 1 minus? You did it last time, Jacob. Anybody else? Olivia? Yes, absolutely right. 1 minus p x is less than or equal to 5. Okay? Interpret the question. No more than 3. What does that mean in terms of our probability notation? Let's go. Perfect. The calculation for everybody, perfect. Right? Not too difficult to interpret that one. At least 7. What does that mean? Somebody else? Jamie? Perfect. Greater than or equal to 7, which, if you're using a CG50, is fine. If you're using a class whiz, what are you going to have to do? And again, go on, Carter.
1 minus x is less than or equal to 6.
Perfect. 1 minus x is less than or equal to 6. Brilliant. Okay. Fewer than 10. What does that mean? Someone who hasn't given me an answer yet. Anybody? Fewer than 10? Go on, Tom. Yeah, it's just less than 10, isn't it? X is less than 10. And how do we calculate x is less than 10? Jacob? At less than or equal to 9. Brilliant. All right. At most, 8. Like a quiz this. What's the problem? How do we describe at most 8? Again. Yeah, absolutely. At most 8 means that it could be 8. All right, but it's at most, so we're looking at everything 8 or below. And again, that one is just nice because it's in the form that you can input into a calculator already. So make sure you don't just rush into a question, right? Read it carefully. Make sure you're doing the right things. The calculations in and of themselves are not too difficult, but make sure you're answering the question. And then just check your answer at the end, and you're all good. Yeah, that's it. I'm going to throw that exam question up at the end. Not literally throw it up, but I will put it on the board at the end. You can just work through the stuff that's in the lesson plans area, all right? So say about 20, 23 minutes, something like that, on a bit of binomial distribution. Sorry, I didn't seem to talk for quite a long time then.